Okay, welcome back. Let's pick it up from where we left it yesterday. So basically, let's spend a minute to review what we have done yesterday. Well, the first half of the lecture was more or less devoted to try to convey the idea that macromolecular systems are more or less the prototype of as complex as it can get when it comes to multi-body physical systems. Yes, they're classical, but there are fluctuations that sort of make it look like a little bit like quantum systems in terms of the presence of uncertainty you have to deal with. There are many body interactions because you have pairwise, but also three-body interaction responsible, for instance, for the angles, and that atoms form in a peptide, for instance. Or there are even four-body interactions responsible for the dihedral rotations, which means rotation around chemical bonds. All these interactions are emergent interactions. They are the result of an underlying simple interaction, the Coulomb interaction, applied to an extremely complex system. A large number of electrons orbitating, say, around fixed nuclear position, at least within the so-called Born-Oppenheimer framework we envisioned yesterday, in which you think the nuclei are so heavy that they can be fixed in precise location while we evaluate the energy due to the electronic structure. Remember? So we listed the difficulties. We don't know the Hamiltonian. But even assuming we knew the Hamiltonian, we don't know how to solve the Hamiltonian because the system is characterized by energy barriers, an exponentially large number of them, and entropic barriers. Remember the doors with the tiny opening. And these two things conspired to give a dynamics with multiple time scales, where the shorter time scale is actually extremely short compared to the typical waiting time I have to wait before I see anything interesting happening in my molecular system, such as major conformational transitions. So indeed, we do not know how to solve for the dynamics, but even if you knew how to solve for the dynamics, we would still have to face the problem to interpret the results that typically live in a gigantic dimensional space. And as such, we have to face the problem that we have to figure out how to decide whether two things are alike, even though they're never alike, technically speaking. You take two trajectories, they never are identical, not even at one time, yet they might represent the same process. But what does that even mean, right? So this idea of having to figure out how to make sense of data in a large dimensional system with a finite dimensional brain is yet another challenge that we ultimately will need to tackle. And this set the stage for the entire course. But rather than jumping right into, let me derive the Langevin equation for you, which is a nice prototype of stochastic dynamics, as we shall see, we took a break. And we decided we would spend some time taking a completely different exercise that at this level appears to be out of the blue. And the reason why we want to take this exercise is that we want to take the chance to stop for a moment and think, what does it mean to develop a physical theory, since after all we will have to develop the physical theory for macromolecules. Not only we will have to develop a physical theory for macromolecules, but we will have to do it for macromolecules with a plethora of scales. So the interplay between scales, experiment, and theory will be very much at the front end of our daily menu, so to say. So we'd rather spend a few days, a couple of hours, trying to figure out what actually it means to develop a theory in 2025, meaning after, after, especially as we shall see, the experience with renormalization group theory has sort of shaped the mind of the physicists to frame properly the concept of making sense of complex data. So we embarked in an exercise. We want to solve for the spectrum of a variant of the hydrogen atom. So we have an electron, but for some reason that we don't need to justify, because this is a toy model after all, the Hamiltonian contains an inner part we don't even know. And the idea is we pretend we know the energy levels experimentally. Since this is a synthetic system, there isn't such a thing as experimental energy levels. So instead of experimental energy levels, we will resort to synthetically computed energy levels in a code that knows what the exact form of the potential is, and we will never know it. But now let me just to be very, very concrete, let me tell you what these energy levels actually are, so that really the connection with experiments becomes clear. Not that you need to know, or not that the particular value that I'm going to write on the board will have any particular meaning, but if I make a number, if I draw a number of the board, it looks more in your brain like an experimental result. It's basically the result of a measurement, which in fact was the result of reading and memory allocation in the computer in this case, okay? So the energy levels that we want to reproduce, I'm going to list them here to the extent that we actually will care. You will find them all written up in the notes that I sent you. So you don't really need to do that, but I write them for consistency, since this also goes on the web. And we go here, 6 as 0.01, all the way to 10s 0.005, and then even have a 20s 0.001. Now, what do we have to sort of take from this table? Well, first of all, something that we already mentioned yesterday, as we go from the ground state up to next to the continuum thresholds, energy level differences become smaller and smaller. In other words, the energy levels become denser and denser. Okay? So there are in fact a large, virtually infinite number of energy levels in the continuum. They are not infinite because the code that was designed to compute them has a finite resolution, just as much as the experiment has a finite resolution. Okay? But here they are. They are all S waves. And the first thing we did was to try to see how much of the spectrum we could reproduce by ignoring the part of the hydrogen Hamiltonian that we don't really know. So if I write this up, this is my Hamiltonian. Let me write it a little bit loud. Remember, I'm using units. In which h bar and masses are all units. I don't care. These are Bohr units if you want. There is this core potential, which is a radial potential, and there is this 1 over r potential. Again, I'm setting E equal 1, m equal 1, h bar equal 1, and even pi equal 1. This is called the trigonometric units. No, I'm joking. Pi cannot be 1. You cannot freely set geometric constant to 1. You're only free to set units to 1. Okay? Okay, so the first thing we tried to do was to ignore this part altogether. So now, instead of writing the results in the form that I used yesterday. I now use a slightly different way of representing them, which is equally good. Is the relative error you're making with respect to the exact value. Since we know the exact value, because they are listed in this table, and then we can compute the values from the hydrogen atom theory. You open up your Sakurai or whatever book you want, and you read them up. The famous 1/n squared formula should hold, right? And then you recompile them all. Now, if you do that, a way to plot the result is in the modulus of delta E over E. I'm not interested in whether I'm undershooting or overshooting. And I can get the energies. These are, of course, negative energies. These are binding energies. Of course, the real energy is negative. The ground state is the most negative energy, right? Obviously. These are binding energies. Now, I can put the binding energy on this axis. The largest value would be the ground state. So in some units, let me put logarithmic units here, because you see I go from 1 to 10 to the minus 3. If I were to put linear units, this would be very, very difficult to plot. So this is 1, 10 to the minus 1, 10 to the minus 2, and 10 to the minus 3. And if I were to show the results that I get by the pure Coulombic interaction, I get a relative error, so that's 1, 10%, 1%, and let me stop at 1 per mil. You can go even below that, but at the moment I'm not interested in. And if you go to compute the ground state energy here, because you see S1 state is of order 1, slightly larger than 1 actually, so this should be moved slightly to the right. Right? You may, by using only the Coulomb energy, you make an error which is of the order of 100%. The relative error is as large as the true value E naught. These are E naught. Okay? You see me? The fact that this guy is of order 1, it says that with just this part, I'm completely wrong in the ground state. Totally wrong. So there is an important contribution from the ground state, from the UC potential. Okay? But as I get down now to the states, now I'm drawing a line. I should draw a collection of circles, if you remember, 1 for each energy level, but I'm not bothering to do that. As I go down to say 1, 2, 3, 4, 5, 6 state, the 6th state, I go down to something of the order of 10 to the minus 2, right? Yeah. And an error of roughly 10%. That's S6, 6S. 6S. S1S state and 6X state. And of course, in between, there are all the other states that are like circles here that I will not bother to write. So what did we learn from this curve last night? We learned from this curve that as I go closer to excited states where the wave function spreads for broader and broader regions, becomes broader and broader, then the accuracy, the error that you're making, drops to some 10%. You're getting more accurate for the broad states than you were for the tight states, right? Yesterday we were plotting the calculated value versus the exact value, and it was going towards 1. Now we are plotting the error. I'm switching from one to the other because I realized that in the Lapage notes, that's the way it plots the data, so I think it's easier for you if you want to reconvey this information in the book. Okay? So what did we conclude from this? We did conclude that the hardcore, the UC potential is shorter range than the Coulomb potential, because it works better and better when you get larger and larger systems. Okay, so enough for being neglectful and closing our eyes to the fact that there is such a potential. Now, we really want to do better than 10% at most, right? So we set up to try to do better. And the way to do better was to approximate these. You see, our first attempt is what people in phenomenology have always been done as a first step. You know, you approach a system you don't know, and you try to make a model that is simple enough to be solved, but rich enough for bringing in physics that you were missing, right? And after some discussion with you, we tried attempt number 1. Well, take UC of R being constant time a delta function of R. Why a delta function? Because it's the simplest way to embody the information. There is a short distance core. And we don't know whether it's attractive or repulsive. We don't know the signs of this constancy. We don't even know the strength. I presume it's not a small perturbation because it gives you an effect of order 100% here. At least on the ground state, it is not a small perturbation. It might be a small perturbation on the excited states. Why? Because if it's short range, the amount of wave function that when you compute the expectation value of the potential, you will always have your wave function, your UC of R, your wave function. And if your wave function spends very little time in the center, now these are three-dimensional R's in principle. I'm not going now to spherical coordinates, which is the right thing to do. But if I were to do this and go to the spherical coordinate, this would drop a Jacobian, which goes to 0 in the origin. Right? Except, that, so in other words, what this guy would give you is a very tiny competition between the delta function that wants to pop up the wave function in the origin. Sorry, the potential that wants to pick up the value of the wave function in the origin, and the fact that wave functions, the fraction of wave function near the origin becomes smaller and smaller if your wave function is broader and broader. Right? So maybe for large states, it is a small perturbation. Okay? So we did that, and after doing this calculation, which we didn't, you get something much, much better. So something that drops from, say, 10 to the minus. So I'm going to write with cross the results of this theory here. Now, look, one thing that I didn't emphasize yesterday for the sake of practical time constraints, this phenomenological model contains a new parameter, C. And we have to fix it somewhat, right? So we have to sacrifice one of the points in this table to fix C, right? We fix it in order to match one of these points. And then we predict all the others. That's always the game in physics, right? Whenever you have a dimensionful quantity, you have to sacrifice some experiments to fix it. Now, of course, if you're doing QED, you can measure the charge and then worry about something completely different. But here, all we have is these energy levels, so the only experiment we can sacrifice is one of these energy levels. So of course, which data do we sacrifice? Well, it's very reasonable to use one of the points where I think my theory is most correct to fit the parameters. So rather than fitting the parameter on the ground state where I don't know because the ground state is extremely sensitive, maybe I want to fit it on this. You see? Why do I want to do that? Because after all, the theory is perturbative for the large states, and for the large states the theory is perturbative, I can use first order perturbation theory to evaluate the corrections, right? Which is extremely simple for a delta function, just the value of the wave function at the origin. Okay? Well, suppose you do it, you sacrifice some of the points here, say the S20, and you predict all others. But what happens? You get a curve that is much better. It drops to somewhere between 10 to the minus 1 to 10 to the minus 3. So it starts from almost 10 to the minus 1. Before it was 10 to the 1. So even in the ground state, you have now an uncertainty of 10%. Okay? And then it goes better and better as I go to the larger extent states. Cool. There are two major flows in this, which we might be willing to close our eyes on. And people do close their eyes on these flows in real life because, like Feynman used to put it, if you are in the jungle, you get sick, there is no doctor around, your best option is the witch of the local tribe. Maybe by making some herbs that he just discovered by serendipity, maybe it implicitly embodies some active principle in some plants and you might be saved. Okay, so this is to say that it is not entirely correct to use, first of all, to use perturbation theory. Why? Because even on the ground state, I have huge improvement. Now, if I have a theory such that the unperturbed theory has an error of 100%, and the first order perturbation gives me an error of 10%, it is, strictly speaking, completely wrong to claim I fixed the problem with my small perturbation, because it means it is not a small perturbation. And maybe the second order correction can be as large as the first one, and the perturbative series doesn't converge. Spoiler alert, the perturbative series never converges. It's only asymptotic. So it gets better for a while, then it screws up. But even if we close our eyes to that, so we wouldn't really be entitled to do that. But maybe here, yes, let's close our eyes. Let's go to the witch and not worry about the fact that we are doing perturbation theory on a theory that shouldn't be perturbative after all. There are worse crimes in physics than this. Okay? But the real conceptual problem comes when we say, okay, I have a way to check whether my perturbation theory is reliable. I compare unperturbed, perturbed, and second order perturbed results. And they should be ordered and become smaller and smaller. They should, in absolute value at least. Now they oscillate typically, if you remember your quantum mechanical course. But in absolute value, they should go down. And therefore, the last difference should give you an upper bound of the next correction you expect to have, if things are well and under control. So we say, why don't we set up the second order perturbation theory? Okay? And I didn't do the entire calculation because this is not a course on quantum mechanics and a sort of resort on your remembrance from the quantum mechanics course, and it's not really important if you don't remember. Let me tell you that if you use the quantum mechanical formula for the second order perturbation theory, you have to include all the states that can couple to your two unperturbed states in an energy denominator, right? Now, it so happens that there are also continuous states, and they are very up in the continuous states. Now, if you have a particle with a huge energy that flies, an electron which has a lot of kinetic energy flies near the center of this atom, if it's very, very, very slow, it can get attracted to it and be bound. But if it's extremely energetic, it couldn't care less, go straight like an arrow, right? This is why we can do X-rays pictures of our bones, after all, right? So all of those very high energy states are totally decoupled. So when we, not decoupled, sorry, they are basically plane waves. That's what I want to say. They basically look like plane waves. If you put a plane wave into the IPX, into the equation, you get a divergence. Why? Because delta function of IPX is that will give me 1 infinitely many times, and you get a divergence. Okay? That sucks. The second order correction is not only not smaller than the first order correction, it is actually infinite. It couldn't be less promising than that, you would agree, right? And we discussed yesterday that this is normally the case when physics is trying to tell you something. It's trying to tell you you're doing something wrong. And we have to figure out what to do with it, what to make out of this. And we sort of reason that the delta function has a very particular meaning. It's a statement of zero range interaction. But you can never say interaction is literally local. Of course, you can make a delta function approximation, but you'll never be entitled to verify that experimentally, because it would take an infinite momentum to resolve an infinitely short distance. And this brings back the entire idea of, I mean, I'm still a fan of the Copenhagen interpretation, in spite of the fact that now the many world interpretation is very popular. They all give the same results, right? Mostly popularized by Marvel movies. No, joking, there are serious people behind it. So I like the Copenhagen interpretation because it roots very well in what we are saying. Because you see, what comes out from this discussion is physics is not about making prediction about nature. Not at all. It's making prediction about measuring nature. You cannot decouple the Hamiltonian from the fact that somebody will ultimately have to measure that. Now, in my personal view, this is humbling because Einstein didn't like it. But it matches very much the idea of the Copenhagen interpretation, right? Remember the Copenhagen interpretation. The wave function is the result of performing an experiment in the system. Okay? Okay, so, and that's where we stopped yesterday. We understood what we did wrong. Now we need to figure out what to do well. Right? Before I go into this, I will draw this again. I want to leave those numbers there simply because it took me some time to draw them. And I want to erase here, but I'm figuring that I don't have an eraser. So I need to go and hunt for one. Let me just put this on hold. No, I'm not going to put this on hold. Okay, sorry. Now I have my beautiful eraser. Okay, any questions so far? Before I go into the next step, let me tell you, yesterday I was reviewing the lecture when I was putting on YouTube, and I realized that there was when we did the discussion about our brain not to be able to process multidimensional, I used the word we were designed to process three-dimensional and two-dimensional. It goes without saying that I meant designed by evolution. Selected rather than designed. But since this goes on YouTube, you never know. The people claim, he's a creationist. By no means. I meant evolutionarily selected to process three-dimensional information. Designed by evolution. Okay, so we cannot claim infinite range. Why? Because we have a finite resolution. So the first thing we want to do is to get rid of any ingredient in the theory we have no control on. Do you agree? So the first thing we want to chop off Hilbert space and get rid of the coupling to all high momentum components from low momentum components, because those high momentum components, if you start from low momentum components, will never be testable, right? This idea that before I even start, let me get rid of large momentum components is called regularization. It's the first step of building a theory. Regularize it. And how do I regularize? I regularize by a called smoothing operator. Well, the fact that it's called operator, the fact that how technical this is done, this is going to be a more practical course than I thought, so I will indulge less into the operator nature of this, and I will be far more practical. So for instance, we have a Hamiltonian, we have kinetic energy, and we have a potential energy. Let's take the potential energy for a moment. Potential energy, I call it U actually, not P. The potential energy, what do? I go to Fourier space, where I have momenta. I introduce a cutoff that chops off high momentum components, and a Fourier transform back. Okay? Makes sense, right? So basically what I say that this is the inverse Fourier transform of my Fourier transform potential, but I introduce a cutoff that only accounts for momentum up to a certain maximum level. Okay, and how do I do that? I have plenty of ways to do that. The simplest way to do that is to put a Gaussian here. Now, this gets very much crowded, so let me rewrite it as E. Let me put a Gaussian here, lambda squared, E squared half, for instance. Why half? Because it's easy to do Gaussian integrals if there is a half. Okay? And then, of course, here I have U tilde of P, which is the Fourier transform of my potential. Okay? Do you read it? This goes down. I cannot believe it. Do you read it? Great. So, in particular, for the Coulomb potential, which I had a bad idea to call the core part C, so I cannot use C for the Coulomb potential. So let me call U naught the Coulomb potential. Do you remember what is the Fourier transform of the Coulomb potential? Come on, not difficult. No? Fourier transform 1 over R Okay, it's typical exercise of advanced of mathematical method for physics. You solve it with the contour integral and residue, blah 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 blah. Is 1/p². Modulus on pi is that I don't care. Okay. So now things are well controlled because yes, you see a divergence here, but there's a Jacobian here. Don't forget about that. And so now this is an integral that actually is almost computable. It's an error function, in fact. So if you were to do that, so basically the result now is something that explicitly depends on the cutoff, right? You see it? So now this regularized potential will depend on the cutoff, right? Because if I choose a different value here, I get a different number here. And now we really are back to Daniele, correct? Or Davide? Davide. To Davide's point yesterday. Yes, the physical theory is intimately intertwined with experiments at the level that even the definition of the Hamiltonian somehow knows about the experiment. And specifically the resolution of the experiment. Okay? Now, this quantity, let me write it here, is known, and I will write it down, is 2/√pi. Forget about how you get this, I don't really care. And then it's the error function erf of r divided by √2 lambda, and everything divided by r. And there's a negative sign. Now, it makes sense? Yes?
I didn't get why we put 1/p² in the place of...
Because I write the potential as the inverse Fourier transform of its Fourier transform. 1/p² is the Fourier transform of 1/r. So this is the Coulomb potential. You can say Coulomb potential is the inverse Fourier transform of the Fourier transform of the Coulomb potential. So it's the inverse Fourier transform of, what is the Fourier transform of the Coulomb potential? 1/p².
So U is the Coulomb potential, not
Yes.
the potential.
U is the Coulomb potential. I didn't call you C, but
Okay.
for the reason that C stands for core, I have the ability of choosing the words notation and the words naming, but it will be propagating throughout the course. I hope you follow me anyway, and you stop me if you don't. So if I don't put any letter, it's the Coulomb potential at this level, okay? And then when it will be the core, I will put the C, okay? But now the point is the following. When I Fourier transform back, I must put this scale lambda. Okay? Do you agree? And when I propagate that parameter, I no longer have a Coulomb potential. I have an error function. Guys, we are saying something quite dramatic here. We are saying that the Coulomb potential was wrong. How come? Can the Coulomb potential be wrong? No, of course not. It follows from gauge symmetry. Right? Maybe you remember, Maxwell's equations follow from gauge symmetry in a modern perspective. They were not discovered by imposing gauge symmetry. They were discovered by experiment, basically, and then Maxwell put them together, and then people realized there was this symmetry called gauge symmetry. But then people in the second half of the century say, oh, they came up with the idea of gauge theory, right? You give me the gauge symmetry and I'll tell you what theory it is. And then they have U1, electromagnetic, then you have SU2 cross U1, electroweak, and then you have SU3, QCD, blah, 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 blah. Okay, you don't need to worry about that if you're a biophysicist, of course. But nevertheless, yes?
I didn't get why we put inside the Fourier transformation that
Because this is a cutoff we put by hand to remove large momentum component because we don't trust our results at large momentum.
Okay,
Because we can only access the theory at finite resolution. Okay?
because large momentum means
Small, yes.
small,
Yeah, I gave for granted the uncertainty principle.
Yeah, okay.
Which, by the way, it is not something that only the uncertainty principle is not only there in quantum mechanics. The uncertainty principle is a property of Fourier transforms. It's not a property of quantum mechanics. Right? You need large momentum Fourier components to get short distance physics right in a Fourier transform. Since the wave function has position and coordinate representation and they are conjugate by Fourier transform, it follows the uncertainty principle. Sorry, English. The uncertainty principle that Heisenberg proposed follows. But that's not because it's a property of nature, but it's a property of the fact that nature has wave function, if you want. And wave function are connected by Fourier transform. So it applies also to Fourier transform beyond classical quantum mechanics. Right? It is called the sampling theorem in other contexts, in fact. Okay, great. Now, what happens? It happens that, is the Coulomb potential wrong? No. I'm not saying the Coulomb potential is wrong. I want to insist on this because this is the heart of doing physics, guys. And really, it is important, even if you are a biophysicist, which you'll probably not worry about any gauge theory in the rest of your life. It is important anytime we write down a physical model, we think deep. We don't overlook at certain problems. We did not put the fact that we put a parameter because we know that we will not be able to test the model with infinite accuracy. But then it's up to us to choose what the parameter is. And if I have a fantastic accelerator to test this, the parameter will jump up to the sky to a point that for all practical purposes, this will be 1. You see lambda going to 0. This error function will basically become Coulomb. Okay? And when everything becomes Coulomb, it means that I will not be able to distinguish my prediction for that of a Coulomb. And if I underline theory that dictated the Coulomb nature was the one that I believed, I'm happy because it says I have principles that tell me it should be Coulomb. I cannot resolve this to infinite accuracy. I put a cutoff. But after that, I do higher and higher energy experiment, and I still keep seeing that it's still the dominant part is the Coulomb part. Yes, I was right, it's Coulomb. You see the reasoning? Okay? Up to my accuracy. Never to all accuracies.
So we can Coulomb if we succeed in measure the potential with infinite accuracy.
Which will never. It is Coulomb up to lambda.
Okay.
So if you can push lambda up to that, you can never resolve any deviation from Coulomb. Okay? Now, these considerations are very relevant in high energy physics. But when we will build Markov models of protein dynamics, in which we forget about each atom and we consider states in which the protein can jump from one state to another, each state will have microscopic configuration, but we give up resolving that. What we are actually doing, we are keeping lambda finite. Okay? And getting an effective, low resolution representation of a much more complex dynamics. And this will answer the question, through which door has the chalk gone? In a very efficient way, as we shall see. So all of this seemingly high energy physics concept, I encourage you to break your head, to wrap your head around it. Because you will see tools that are practitioners tool under a different perspective if you spend the energy, the mental energy to go through this. Okay, so bear with me. Okay, now, what about the kinetic energy? Now, I will use an heuristic argument here. I can do commutators and show you everything, but this is not a quantum mechanical class. But I think there's no point to regularize the kinetic energy. Why? Because you want to avoid the coupling between low momentum and large momentum, right? Because you only want the theory to be confined into the low momentum space, the large distance space, right? Now, the kinetic energy operator is diagonal in momentum space. It's diagonal because it's p square. It's diagonal in momentum space. A diagonal operator will never couple, by definition, different momentum operators. So you never generate high momentum components starting from low momentum components. You can put a cutoff, but it's useless. So let's not put a cutoff altogether. There's no point to regularize kinetic energy. Okay? So, on the other hand, but this makes sense because if your Hamiltonian only contained the kinetic energy, you would never be able to measure it. Because in order to measure something, you have to interact with something. Right? Okay, good. But now comes the difficult part. We have regularized everything we had in the Hamiltonian. Now comes the momentum, the core part. And here is where the magic happens, guys. Can I erase? Are there questions? What about UC lambda? Now I want to regularize UC lambda. Okay? Well, let's do the same game, right? We write UC as the inverse Fourier transform of its Fourier transform, where we put okay? But now comes the most important and dramatic point of the entire discussion. I am interested only, now stop writing, finish writing, and then look at me when you're done. Look at the sun. Is it large or is it small? Answer. Is the sun large or small? Huh? On what?
On where you are when you look at it.
Very good. If I look at the sun from here, all I see is basically, I see actually a sphere with a radius, so it's not entirely a point. If I look at Alpha Centauri, I see only a point. But if I were able to travel 7 minutes at the speed of light and get close to it, hell not is small, it's a huge star. And a star with a lot of structure. The solar flares, the explosions, a lot of dynamics going on the surface of the sun, which I care none about if I'm here. Which is not to say that I don't care about that dynamics in all respect, because I'm alive because of all those explosions. Right? So I experience the fact that the sun is not a small ball, is actually a huge amount of burning helium. But I'm totally insensitive to the details of that physics. The long distance physics is insensitive, not to the short distance physics altogether. The fact that you have a nucleus inside an atom makes a hell of a difference. if you had any, right? But what you're not interested in is the details of the short distance physics. Another very classical example is the multiple expansion. Remember, monopole, dipole, quadrupole. If your distance is very large compared to the distance where the electric charge is confined, you don't care about solving the Laplace equation with the integral equation, remember that you have to do. All you care is to put in a few constants, which you can either measure or compute from the charge, and you would be accurate to any desired accuracy with a finite number of constants, right? Because all of the inner physics that goes inside is details that become irrelevant at a large level. Physics starts when you can say something is much larger than something else. Remember yesterday? Put them in relation. So as long as I'm very far from the sun, I can ignore helium nucleus fusion, and just care about how much energy gets deposited on my plate per unit time, which I need to care about. If I'm studying atomic physics, I don't need to care about nuclear physics. All I need to care is there's a charge with a given mass in the center of the atom, right? So here, going back to this example, as long as I'm interested in the far large part of the spectrum, and I don't demand to myself to be able to resolve all of the spectrum, to go to arbitrary short physics, which is the equivalent to get close to the sun or to get close to the charge distribution, I can ignore short distance physics, right? Now, if you think about it, this is equivalent to say that I only retain low momentum components, right? I'm only interested in very, 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 very soft modes. Do you agree? But if I'm only interested in the soft mode, I can expand this integer series of P. Why not? So I can write U tilde of P will be some constant C naught plus, what's the first order? In principle, it would be something like multiplying P, right? Linear, and then there would be 1 multiplying P squared, okay? Actually, Pi, Pj in principle. But I can neglect some of these terms in this state of expansion because, and now listen to me, I know I have a magic ingredient, I have axe in my sleeves, and the axe in my sleeve is called symmetry. In particular, I know that my Coulomb interaction is, my interaction must be Galilean invariant in this case, meaning that the laws of physics should not change if I look at an atom from this side or from this angle, which means that the potential must be rotational invariant at this level. And clearly, if this is a vector, the coefficient must be a vector, but this is not rotational invariant because the rotation of a momentum gives you another momentum. Okay? So I will neglect all linear terms. Similarly, I will not have a nation here. I will have a square, a Laplacian, because a Laplacian is rotational invariant. A quadratic form with a Hessian Pi, Hij, Pj is not. Okay? Do you follow me? So I can say Phi2, and I have only quadratic terms. You see, I already gotten rid of a number. And just as much as in that multiple expansion, to any finite accuracy, I only need a finite number of terms. Here, to any finite accuracy, I only need a finite number of these. Okay? This is magic because we had no idea of what the core potential was before we started, and we will not know. But only exploiting the fact that there is a decoupling of scales we can go a very long way in inferring the relevant structure, the mathematical structure of the potential that really needs. It's not a true function. It's not. I'm not specifying the potential here. I'm only saying that its Fourier transform, the modes that should dominate are this, and I don't know this constant, the d. Okay? And now you should start to see why I took the pain to get you some extra quantum mechanics, even though many of you probably went to this course precisely not to have to deal with quantum mechanics ever again in their life. Because quantum mechanics has these nice things that has Fourier transform inside, in and out. I mean, they're really built into quantum mechanics. So I don't need to motivate to you why I'm doing Fourier transform in quantum mechanics, right? You have digested that already. However, now we go back to what we said at the beginning of our lectures. Lecture 1, macromolecular dynamics is characterized by very many, very much separated scales. So that means that I don't need to worry about the inner scale as long as I'm interested in the dynamics of the outer scale, and there's a gap. So I will be entitled not to care about some physics, even though it's there. And I can even make a mistake, guess a wrong functional form, as long as that functional form will contain the right momentum components, I'll be only sensitive to those. Okay? So, stated differently, I could guess 2 different charge distributions. Suppose I give you 2 different charge distributions that to some incredible accuracy have the same monopole and dipole term. Only one of the 2 is the true charge distribution. The other one I made up. But I made it up in such a way that would give me the same dipole and the same monopole. If I am far enough from the charge, I'll never be able to distinguish which one is the true one. I can use either of them. Do you agree? The short distance details is not relevant at large distance. Similarly, now you see why I'm taking the pain of doing all this. The force fields, remember the problem number 1, we don't know the force field. But we don't really know. We only need to have enough information about the long distance physics of the force field. Unless we really want to study vibration of atoms or angle bending, which are really, by the way, quantum mechanical, so we shouldn't. But as long as I'm interested in global movement of my peptide, this is the equivalence of looking at the charge distribution for very much apart, or to carry about the 20th energy levels in this theory. I don't need to know the detail of the potential. I can get any potential, fits the data, as long as he has the right Fourier components. Okay? You see why this is central if you want to study multi-scale system. Okay, great. But now it's even cooler, because you see, what happens if I take a C naught and I go back? I can anti-Fourier transform, and it's the anti-Fourier transform of a Gaussian. What is the anti-Fourier transform of a Gaussian? A Gaussian, which looks like a delta function, but it's a representation of delta function with a finite smearing of size resolution. Now we are talking. If I have a finite resolution, I cannot say the delta function is the right choice. It's the smear delta function the right choice. And if you have a smear delta function, you don't have infinities because you don't couple to large momentum components. So the famous plane waves that were screwing you up, off they go, right? Great. So let's stick to C naught. And by the way, the next term is inverse Fourier transform of p squared. And if you think about it, the inverse Fourier transform of p squared is you know the property of Fourier transform, the inverse Fourier transform of p squared function is the Laplacian of the Fourier transform of the function. Remember that? That you can turn each p squared into a gradient. That's why the momentum operator is e to the negative I h bar gradient, by the way. It's simply because of that, right? So when I go back to position, this would be constant times delta function is mirrored to the scale lambda, which is a Gaussian of size lambda, plus C2 gradient square of the delta function of scale lambda. And this is not as bad looking as the Laplacian of a real delta function, because the Laplacian of a real delta function is an ugly object. It only makes sense when you act by part on the test function. Remember the concept of delta function. But the second derivative of a smear delta function is the second derivative of a Gaussian. It's a perfectly fine, healthy, fast decaying function. Okay? Now, we have introduced these objects. We're almost done. What are these constants? I have no idea. I have no idea. We just postulated them, right? Is it your hand up?
Yeah.
Ah, okay.
I'm not fully understanding how we applied the symmetry argument. So we applied on the Coulomb potential or on the core.
Okay.
So
If your states are still fixed angular momentum states, I'm giving you a slightly more formal argument than my hand waving Galilean invariance, which is correct, but I give you a different argument. I've listed S-wave states. It means angular momentum is a good quantum number. For angular momentum to be a good quantum number, it must be conserved. For angular momentum to be conserved, you need rotational invariance. So your Hamiltonian must be rotational invariant. If I had put a P here, now I erased it, a linear term in momentum is not rotational invariant, because if I rotate the momentum, I get a different momentum. For the same reason, if I have Hij, Pi, Pj, both Pi and Pj get rotated. But the norm is invariant under rotation. Okay? So I'm using this symmetry thing to postulate only certain terms. Well, the worst comes to the worst, I put the others, if I'm not sure about the symmetry. Okay? Okay, so what happens now? I have to fix this. So what does it mean to fix? What does it mean to fix one of these components? So let's take the first approach. Let's forget about this and take the monopole in this analogy. Okay, so the lowest term, which means the decoupling between the short distance physics and the large distance physics is very large, because, as you know, if I had to include more terms, it means that in the case of a multipolar expansion, I'm getting closer to the charge. So the decoupling of scales is worse and worse. When the decoupling is very large, I only put a charge there and I'm done, right? So let's assume the hardcore is very short range. I have to fit one parameter, as before. I fit it to one state. Now, I said something and nobody objected this. But this is called renormalized my parameter, meaning I fit it. After I fit my parameter, though, my potential is determined, and I can use it to evaluate whatever I want. Okay? So now everything is finite after regularization, and step 2 is renormalization. It just fit. So now remember, I wrote step 2, fit, which means fit the parameter to data. Remember what I told you yesterday. There is such a thing called QED. QED people did calculations, found infinities, collected all the infinities in one side, and you have a quantity that would become infinity if you would let a parameter go to infinity, which is a momentum parameter, by the way. But you keep it finite and you replace it with a charge. We are doing exactly the same here. We have removed the infinity components, kept a regulator because we don't have to worry about those physics because we don't have way to access all possible physics. So we should exclude that. Not we might, we should. And after we have done it, of course we have to fit a parameter. That's physics, you have to know some parameters. Nobody tells you what the mass of the electron is. The standard model, beautiful standard model, has 27 fit parameters, which you cannot get rid of, okay? So if you do, and you go back to that famous, how does this do? So let's go back to our famous curve. Now I'm gonna be more sketchy. I will not draw all the points, all the details than before. You got a point. So let me just draw qualitatively. Delta E over E naught in modulus. Here are the energy levels. And the more you go to the right, sorry, this is the energy. The more you get here, the more you have deeper binding energies. So remember, these very bad, poor Coulomb. 0 parameters though. Delta function, phenomenological. Yes, 1 parameter, but it screws up a second order perturbation theory. Now, instead of doing delta function with 1 parameter, let me do smear delta function with 1 parameter. So I'm not fitting more parameters. I'm using the same number of parameters, but now I've done things the proper way. And just by doing this, you increase by order of magnitude. And if you put 2 parameters in the proper way, you go down by 1 part over 1,000 in no time. Even using perturbation theory. So there will be an endless discussion as why perturbation theory works so well, but which is super interesting but far from your interests, and so we'll not go into it. What I want really to stop and think with you is, what have we learned in this exercise? Well, first of all, we've learned that doing physics, that a physical theory is a combination of some mathematical formula that describes the dynamics and so on. Or if this is not a dynamical problem, I don't have a time-dependent, Schrödinger equation. I have a static Schrödinger equation, which means that I'm only interested in energy levels. Fine. Whatever is the object of my theory, okay? And I have a scale. And the next question in the scale is to the maximum accuracy I want to reach with this theory. I need these 2 ingredients. I want the theory and the maximum accuracy I want to reach with this theory. And I already know that whatever theory I do, there will be a maximum accuracy beyond which it won't be meaningful anymore. Because I'm using formulas that only apply to the low P sector of my theory to describe the high P sector of the theory. So throughout the course we will use a jargon that is taken from optics, but of course has nothing to do with optics. We will refer to the infrared sector of the theory as the low energy, low resolution part that we are interested in studying, the part far below the cutoff, and the ultraviolet sector of the physics as the part that we ignore. Now, if the ultraviolet and the infrared part are very, very, very close apart, physics gets harder and harder and harder to formulate. To the point that when they touch, there is no physics. Sorry. You see what I mean? If it's all a continuum of scales, there is no physics. Physics only begins if you can find gaps between new dynamics and new dynamics and new dynamics. So, in other words, physics is something like an infinite store building, which is a very weird one. So this is physics. You have a ground, some trees, and you have an infinite store building. Why infinite store? Because not really infinite is as long as my resolution will keep on growing, can look at higher and higher stores on the building. Because I will be able to reach and see what is the structure of the building up in the sky. Right? In the ground are the low energy levels, up are the other levels. So here's my skyscraper. Normal skyscraper have windows, evenly distributed unless the architect was under dope during design. But physics is a different building. He has a lot of windows here, all piled up here. Then nothing. And then another bunch of windows here. Now, sorry for drawing windows really, really bad, but you get a point, right? And then nothing again for 100 stairs, and then more windows there. And anytime you try to make a physical theory, you must put a cutoff in between them. Because if you put a cutoff here right here, of course, depending on how you really tune the cutoff, you are putting in or putting out some physics that you shouldn't really discard because they are all similar, right? So it only makes sense to put a cutoff in between this and then say, I can neglect of all this physics, the details of all this physics, not the fact that there is such physics. The sun shines on the earth, but the details of the solar flare and the solar whatever it is are not interesting for me. If I'm interested in understanding how a cell gets its cycle out of the energy of the sun, bacterial cell, okay? So, this part is called the ultraviolet, and this part is called the infrared. And by definition, physics is always about the infrared of some ultraviolet. Yeah? Like we're always southern inhabitants of some northern country, right? Now, going back to macromolecules, this starts to be interesting now. I'm not interested in the physics at the femtometer scale, femtosecond scale. First of all, it should be quantum physics at that scale. So if I really wanted to do quantum physics, if I really wanted to account for the physics at the femtometer square, I should do quantum mechanics. But now I can raise a question that if I had reason, if I had put up yesterday, probably would have sounded confusing to you. So I put it up now. I told you yesterday that in order to describe correctly the fact that atoms don't overlap, you have to use the femtosecond integration scale, right? Because things have to go smoothly. If they make big jumps, no good for integration of differential equations, right? But at the femtometer scale, femtosecond scale, I am not entitled to use Schrödinger equations, strictly speaking, because that is quantum physics at that time. So why can I use classical molecular dynamics with femtoseconds integrated time scale if the physics is wrong? Do you follow my question? Do you follow now? Raise your hand. Do you agree that if I want to integrate the Newton's equation for macromolecules, if the potential is very hard, I have to take time steps that are very small? Right. Potential very stiff, small time step. Now, it turns out that to account for the stiffness of van der Waals, the integration time step must be at least a femtosecond. Okay? But if I were to describe the dynamics of atoms at the femtosecond time scale, I would need quantum mechanics. But I don't do quantum mechanics, I do classical dynamics. So you might wonder, I'm summing many wrong physics to get the right physics? How can I do the right long-time dynamics by summing many small wrong-time calculations? Do you follow me? Have you ever thought about it? Of course not even needed to die before I thought about it. And the reason is that this applies not only to molecular dynamics, it applies to anything. Right? If you go even shorter, you will need ground unification at some point, right? Or whatever there is, string theory. But we don't have that theory yet. We make small integration and we pretend it works. We can, because physics is an infinite store building with cluster windows. So if I'm interested only in here, I do not need to know the details of the ultraviolet physics. So I can take an entirely wrong ultraviolet physics, which produces the same infrared physics, integrate that as long as I don't use it to study femtoseconds dynamics. So I can use the wrong physics as long as there is a decoupling of scales. If there was no decoupling of scales, this would be entirely wrong. But thanks God there is a decoupling of scale. The short distance physics is very different from the long distance physics. I can use the Newton's equation all the way through. Because it's like, it will give me one of these theories that will ultimately produce the right momentum components. So the low energy predictions that I'm going to use this theory for will be insensitive to the short distance focus once I have fit the parameters, of course. In other words, if I've chosen the parameters of my model to reproduce the data. So this is fundamental to understand that, yes, we don't know the force field and we were not actually entitled to use the force fields all the way through. It's very different. I can integrate the equation of motion of a cannonball shot without ever worrying about quantum mechanics. Why? Because I probably need milliseconds time step. I don't know, I'm guessing at. Move a cannonball for a millisecond to integrate properly its motion. And at that scale, that is still perfectly classical. So that doesn't raise this problem. But macromoleculars do, because at the shorter scales, the hardcore are non-classical. But I don't need to worry about this because of this. So all this big discussion to say we can rely on force fields. Are they perfect? No, they probably miss some ingredients to test the correct long-distance physics. There is an industry of people producing force fields. And what do? They change the hard part, but they also change the long part, the Coulomb part. So of course they will produce different predictions in the long time regime. If they were only changing the small part and refitting, we wouldn't know. Okay? Good. You're boiled. I am not going through any new topic today, because this is the part that I wanted to give, so we can have a few questions if you want, or whenever you feel. I'm not going to start. But this closes an introduction. And the reason I wanted to do this introduction, I think, is clear. And it has not simply because of we're going to integrate the equations of motion. It's because it applies to everywhere. When we will write the Langevin equation, we will make the same reasoning. When we will write the overdamped Langevin equation, we will make the same reasoning. When we will go to a Markov state model representation, which ultimately will answer the question, which door is the system going through? So it's relevant. We will do the same reasoning. As long as we're not interested at that particular dynamics, we can put everything under one parameter and move on, move on, move on. This is the way our century, actually the last part of the 20th century, devised this Russian doll view on science and physics, which is super productive because it allows me to rely on something that I don't know to build something that I know. The point is, I don't need to know the details of the Russian doll that is inside my outer doll, as long as I know that there is some global properties to any finite accuracy. Now, if you're a believer that you need infinite accuracy, which to me makes Galileo sort of fumbling in his thumb, but to some people probably makes more sense. It made sense to Einstein, so who am I to question that? But as long as you're interested in any finite accuracy, you're good to go. Certainly in biophysics. We don't have the claim to be infinitely accurate. As long as we get something that is reasonably okay, we're going to go and get drunk, right? So that's particularly relevant for us. Thank you. Unless you have questions, now I'm going to shut this down and we can ask questions if you have.